Okay, people are joining. Welcome, everyone. Give a couple of minutes here for people to get on. Get up to 20 and then we'll. All right. Okay. Welcome, everyone. My name is Josie Crawford, and I'm the Executive Director of the Wolf Creek Community Alliance. Thank you, everyone, for showing up tonight. It's impressive that you're here and shows some of your commitment. So I'm with the Wolf Creek Community Alliance, and our mission is to protect, preserve, and restore the Wolf Creek watershed by increasing knowledge, appreciation, stewardship, and public access to the creek. So part of protecting the creek now is protecting it from the ravages of climate change. We have identified climate change as really the largest threat to our watershed due to droughts, fires, heat, and extreme weather events. So we've all been suffering, plants, animals, and humans, from the relentless fires, the threat of fires, smoke, heat, extreme flooding on years that we have it. Hard to believe that that will ever happen again. Electrical shutdowns, and COVID, which doesn't have much to do with climate change, but still. We've all been experiencing real shortages of it's becoming very real to us. So we're experiencing shortages of water and breathable air. Makes it really real. That's probably why a lot of you are here tonight. So yeah, shortages of electricity, shortages of microchips. It's really becoming obvious that there's a big problem and we need to do something about it. So we want to offer these workshops or webinars to offer a little bit of hope and help us come together as a community and start building resilience right here in River City. So, so we're offering talks by local experts and leaders on building local resiliency and creating some independence, like power and food and keeping our forests healthy. In response to the threats that we have from climate change. We hope to provide some tools and resources for you and expand the work that many local people are already involved in to include people like yourselves. So please join us in creating a more self-sufficient, livable, and healthy set of watersheds. These first two webinars are supported by a grant from the Strong Foundation, but that money has finished and we have gone through it, and we are hoping that some of you or your organizations might want to continue something similar where we're sharing what we're doing together so we can really start to enlist more people. So let's see. We have two wonderful presenters here tonight, and I'm giving a tiny thing in between, but then Jeff Lauder, he's the Executive Director of Sierra Streams Institute. And then about 20 minutes. His talk is called Climate Change Driven Impacts to the Sierra Nevada Ecosystem. And then I'll give a very short description of the Wolf Creek Watershed just to orient you and provide a little background information for David's talk. And then David Whitehead will present challenges we are up against and what actions can we take now. Oops, I said that a little bit off. There was what challenges are we up against and what actions can we? So we're going to ask you to put your questions in the Q&A, and instead of the chat, we're going to be putting other information in the chat, contact information for the speakers and the organizations. I believe that David's got some other things that are going in the chat. We'll also have a few polls. So just try to remember to put your questions in the chat, and we'll answer a few questions. We'll answer questions we'll ask and answer questions after each talk. And then at the end, if there's still more questions for everybody, you can ask anyone what you want. So right now, if I can do it, I'm going to stop this and I'm going to give you the first little poll. And so you can answer this first question, and then I'll give you the results in just a sec. Almost done. Okay, looks like it's not moving, and I'll share the results with you. Looks like most people are already in a group and doing some work, which is fabulous. And then a few of you, how many? 2 out of 15 are not involved yet, but you're interested, and 1 person is not interested in joining a group. Okay. And that's anonymous, by the way. We don't know your answers. Okay, so let's see. I'll go back to, sorry, that was a little awkward, but okay. So Jeff Lauder has a PhD. He's a forest ecologist, and he is no longer the interim, but the executive director of Sierra Streams Institute. It is official. So I think you can send him some, in reactions, I think you can send him some congratulations to his new position. Jeff is a lifelong explorer and researcher of the Sierra Nevada mountains. Born and raised in California, he received his undergraduate and master's degrees from CSU Chico, working in tropical forest ecology. He worked with governmental agencies and nonprofit organizations before completing his dissertation on Sierra Nevada forest response to drought and bark beetles. Jeff has more than 10 years of research experience in the Sierra Nevada, from amphibian ecology in Yosemite National Park to forest ecology across the range. His research interests include examining how climate change has already impacted and may continue to impact Sierra Nevada ecosystems. And so with that, I will turn it over to Jeff.
Yeah, thank you so much, Josie, for the introduction and for putting this webinar together in general. This is great to bring groups together like this to talk about how we can work together toward kind of shared objectives. We've been kind of a partner neighboring organization and watershed to Wolf Creek Community Alliance for a long time with Sierra Streams Institute. Our home watershed, which I'll show you in a little bit, is the Deer Creek watershed, but we do also do work in the Bear River watershed, of which Wolf Creek is a sub watershed component. So it's really nice to be able to come here to talk to you guys about kind of some case studies using the Deer Creek watershed, and then climate change driven impacts to Sierra Nevada ecosystems at large, including some expected and projected change, some observed change, and then a little bit of a touch on forest ecology as well. So a couple different topics wrapped up in today's talk. I want to start with acknowledgement of the Nisenan people. So the land on which we currently conduct research, monitor, work, and live was stolen from the Nevada City Rancheria, Nisenan, and they're currently working to restore federal recognition, an effort in which we greatly support them. I also want to include this because of the significance of Indigenous inhabitation and stewardship of the land to the Sierra when we talk about climate change resilience. So we know that the forests of the Sierra Nevada, the landscapes as a whole, have been stewarded by Indigenous people and lands across California in general for the past 11 to 12,000 years. So their impacts are definitely huge components of considerations of climate change impacts on the landscape. That's especially important when we think about things like fire, which are increasing in frequency and severity, as we're all very familiar with both local fires and some of these larger regional fires. These are both taken from fires from this year. The top left photo is from the Dixie Fire, the bottom from the Caldor. And we know that Indigenous stewardship of the land, including their history of prescribed burning and cultural burning, had significant impacts on forest health, and that removal of prescribed burning from the landscape is an important consideration when we think about climate change impacts, and we'll come back to that in a little bit. But first, wanted just to give a brief introduction of Sierra Streams Institute and kind of us being a neighboring organization and neighboring watershed. We started off in 1995 as Friends of Deer Creek when a group of concerned citizens got together to monitor Deer Creek upstream and downstream of the Pine Street Bridge, which was being reconstructed. Through that process, our founding chemist, John Vanderveen, and a group of dedicated volunteers came up with some protocols and instrumentation to then start monitoring the entire Deer Creek watershed and said, hey, we can actually put kind of this information in the hands of the people and have a watershed monitoring group based on robust science. 2003, we then kind of started expanding our projects a little bit to include not just monitoring, but then following up on that monitoring. So doing things like restoration, research and remediation projects focused on mining contaminants from our history of mine waste in the region, forest health research and management plans, and all of this is under the umbrella of community-based participatory research, which is also taking this educational component, and again, truly trying to give science back to the people and allow us to monitor the ecosystems which we live in. And this led to then by 2010, reincorporating officially as Sierra Streams Institute to reflect kind of our expanded mission. And now we've branched out to monitoring, like I said, the Bear River watershed and some other projects beyond simply Deer Creek. So when we talk about climate change impacts to the Sierra, we have to first talk about climate change impacts globally. So this is a brief kind of refresher on a topic that I'm sure many of you are familiar with. David also touches on some of these figures and has some great descriptions of them, but these are taken from the current year's IPCC annual assessment report, the AR6, which is basically published, but still kind of in press in terms of the publication process. And the top left panel here has two figures in it. The left figure is looking at temperatures going back about 2,000 years. And we now know that the warming we're experiencing in the 1850 through 2020 period is unprecedented in the at least the last 2,000 years. David will touch on how it goes back even farther than that. And then the figure on the top right is looking at the observed versus simulated human and natural contributions to warming, and then actually simulated only natural contributions to warming and the difference in those. So we're talking about attribution to this anthropogenic warming. Numerous studies can then be used to go further into attribution and look at what are some of the specific components that we can trace back to anthropogenic sources that are driving some of this climate change. So this bottom right panel, we have three figures. The left one is showing the increase of about 1 degree Celsius since 1850. And then it further breaks that down. I know it's hard to read, but in the individual components that contribute to that warming. So moving from left to right, we have total human influence and well-mixed greenhouse gases contributing 1 to 1.5 degrees of warming. And then the far right figure breaks that further down into things like carbon dioxide and methane as contributors to warming. And this kind of then just points to two things when we talk about some of the discussions in terms of actions around anthropogenic warming. Well, we know warming is occurring due strictly to some anthropogenic sources based on these attribution studies and based on some basic physical properties of these chemical components that we're injecting into the atmosphere. The more CO2 comes out, the more warming you get. And we focus on carbon dioxide because it's an anthropogenic source. We know that it's coming from us in terms of industrialization, so that's why we focus on it as a potential target. But what does this mean then for the Sierra specifically? Well, this is a report from the UCLA Center for Climate Science, where they also have then aggregated multiple studies over the years looking at climate change impacts on the Sierra specifically. There's a lot of interest here because the Sierra Nevada region makes up 60% of California's freshwater source. We really are the reservoir of the state. So it's hugely important to look at how climate change may impact this reservoir. So the top right, we have two columns. The red column is looking at projections in Sierra snowpack and temperature under the business as usual climate change scenario. And then the blue far right scenario is a mitigation scenario for actually to start minimizing CO2 output. And what we see is under the extreme scenario, or the business as usual scenario, a projected 7-degree rise in average springtime Sierra temperature by the end of the 21st century, 64% drop in snowpack, and a 50-day earlier runoff of snowmelt into streams. And then under the mitigation scenario, we still see a 4-degree rise in springtime temperature, 30% decline in snowpack, and 25-day earlier runoff into streams. And this still happening under a mitigation scenario is because of what we call climate inertia. So there's still kind of this momentum built into the system, even if we ceased all greenhouse gas production today. So those are projections, but what about actual observations? So this is raw data looking back about 100 years since 1906 across the whole state. The top figures are temperature, the bottom figures are moisture, and we can see that mean and minimum temperature have both significantly increased over the last 100 years. Red means warmer, and blue means cooler. Maximum temperatures have actually declined in some portions of the state. So this is really significant when we consider climate change impacts across California, is really it's our colds are becoming less cold. And you see that especially concentrated throughout the Sierra. If we look at precipitation across large portions of the state, we actually have increases, but in the Sierra, it's staying about the same or declining. Combine temperature and precipitation, and we can start to look at what's called evapotranspiration. That's water movement out of the landscape back to the atmosphere, a good measure of kind of aridity, and that's increasing across large portions of the northern portion of the state in particular. And then we can combine all of these into a measure called climatic water deficit. And this is literally the amount of water that we think is essentially missing from the landscape. So how much water is being pulled out that isn't there. So more red means more drought prone or arid. And most of that's concentrated in the southern portion of the state and then along the foothill belt of the Sierra, like where we live here. So with all these things considered, we wanted to take we have 20 years of water quality and biological data across the Deer Creek watershed. So we wanted to say, hey, can we use this 20 years of data and some of the extremes that we've experienced as kind of a case study to ask, do climatic drivers outweigh other drivers, background change, land use change, in determining watershed health from a water quality and biological response perspective? And we can do that because the past 2 decades actually have some extreme climatic events that can help us project how our watershed might respond to similar extremes in the future. So for example, 2012 through 16, we now consider to be one of the hottest droughts in about 1,200 years. This bottom left figure shows that. PDSI's Palmer Drought Severity Index, more negative means more dry, and then precipitation anomaly, more negative means more dry. This is a tree reconstruction going back to 1293. And we see it was the most extreme in over a millennium. So we wondered, can we use these kind of essentially as bookends and say, how did the watershed respond to these extreme years? And can we then use that response to project out how it might respond to similar extremes in the future? I really want to hang on the last word of that second question, though, of climate susceptibility and resilience. This is a topic that David's also going to touch on, and obviously was in the title of kind of the goal of this webinar, is what resilience is. And it's kind of become a buzzword that's tossed around a lot. And we just want to take a second to talk about the definition of resilience and how we might be able to quantify that. And my first exposure to this definition was actually in the realm of tree response to drought. And that's what this figure here is referring to. So this trait on this vertical axis could be something like tree growth, where you have growth over time, and then a stress is applied like drought. The tree growth then declines. If it declines more, the tree is less resistant. If it declines less, the tree is more resistant. But that's not the only component of resilience we're interested in. We're also curious about how an organism or ecosystem can then recover from that stress back to some state that's similar to its original state. So for example, the organism on the left here is more resistant, but less resilient to stress than the organism on the right. So we really have to consider those two components of resilience when we think about climate change susceptibility and resilience. So this is a map of the Deer Creek watershed, your neighboring watershed to the Wolf Creek watershed, and the one that we're using for this case study. We've been monitoring most of the sites listed here for about 2 decades, ranging from the upper watershed above Scott's Flat on the right, all the way down to the confluence with the Yuba on the left. And we measure all of the water quality parameters listed on the left. And some of these we might expect to change under climate change. So some obvious ones would be increasing air and water temperature. That can then lead to things like declining dissolved oxygen, which then can support less biological life because warmer water holds less oxygen. So we wanted to see if this was actually occurring and to what extent. And then we can also look at benthic macroinvertebrates, which we sample biannually. These are bugs in the water that tell us a lot about stream health, because some bugs are more tolerant or less tolerant to certain contaminants or conditions. So if there's more or less of those bugs, then we might use them as an indicator of overall stream health. And then finally, we can use a lot of these more powerful spatial data tools and data sets that are becoming available to us, like remote sensing from satellite imagery. So in this case, we looked at things like land cover in 2001 and 2016 at a very high resolution, and then can break up the watershed into individual catchments. And that's what you see here. And this is where every green dot is a monitoring site, and the polygon around it is everything that flows into that monitoring site within the watershed. So at that catchment scale, we can look at change in forest cover, change in percent impervious surfaces, those kinds of things. And then also get really high resolution canopy cover. So we can look at stream shading, forest density, and those kinds of things across that catchment scale as well. We can then plug all of those things into a very confusing diagram I'll show you here. This is called a structural equation model. And basically a structural equation model, what it's doing is it's taking a conceptual model that we come into something asking, hey, is this how this system might be responding to change? And then we can take real world values to then measure those changes. So for example, climate, water quality, land use, and biological response, these circles, are all kind of these conceptual things we call latent variables. We're not actually measuring them. What we're measuring are individual indicators like climatic water deficit, which is drought, precipitation, maximum temperature. For land use, we can measure impervious surfaces, canopy cover. For water quality, all the things that we measure at all of our sites. And then for biological integrity, we can look at percent intolerant taxa, the ones that can't stand change, percent tolerant taxa, the ones that can withstand contaminants. And then IBI is a single number that represents stream health. It's the index of biotic integrity. And then all these yellow arrows are the different models that we test. So we're saying climate influences water quality, and land use influences water quality, which then influences biological integrity. Or we test all these other alternative models with these, which these dashed lines represent. So we run a whole suite of models and then say which one statistically fits the actual kind of response in our data and best explains how these systems are responding. So I'm going to show you next is this same model, and all that remains are the best fit variables from the best fit model. The green colors represent positive change or interactions, and the red represent negative, and the size of the arrow is kind of the level of significance or the level of response. So climate over the last 20 years has been reflected as increasing drought, increasing temperature, decreasing precipitation, pretty much on par with what we might expect with climate change. That then leads to this positive increase in what's called water quality. That's kind of a misnomer. Water quality itself didn't improve. What happened is we had increasing water temperatures and decreasing dissolved oxygen. Again, kind of as predicted, those are the biggest shifts over the last 20 years. Land use then was best represented by changing forest and canopy cover. Water temperature was then also directly influenced by canopy cover, which is interesting. So we have kind of a shading effect. Land use then influenced biological integrity, but didn't actually influence water quality. And then the resulting change in biological integrity was a decline in overall integrity and a decline in those intolerant bugs, which really need pristine water. So pretty consistent with expectations. We can then take this model though and try to project out into the future. So we can take the various climate change scenarios and models available to the public, pick the ones that best seem to represent and track real change across California from an observational perspective, rebuild the model with the projected change in 100 years, project out our drought for 100 years, and see how might we expect water quality to change across the watershed in 100 years. That's kind of what we have here. This is just a snapshot where basically what you're looking at is each bar is a different climate model showing the projected change in drought or climatic water deficit. So in our upper watershed sites on the right, we actually have some that are cooling or decreasing drought likelihood. And then most of our water quality variables stay the same by about 2100. But our lower watershed sites, all of the different climate models project dramatic changes in climatic water deficit, so increasing aridity, and then corresponding increases in water temperature and crashes and things like dissolved oxygen. So we might expect greatly diminished stream condition in the lower watershed moving forward. We can then look at variability over time and peak observed drought, and to start to get an idea of sites that might then be susceptible or resilient to stress. So for example, sites that have higher observed climatic water deficit and more variable climatic water deficit essentially are really responsive to climate stress moving forward. And then we can combine that with projected increases in drought and aridity to give us actual restoration and management targets. So for example, if we have some sites that are really variable from year to year, but aren't projected to increase much in terms of drought and aridity, those might be good targets for kind of mitigation strategies. So we can focus on maintaining riparian coverage and habitat for stream shading, maintaining biological habitat. Whereas our lower watershed sites, if they're both projected to increase in aridity over time and are variable, those are really targets for really intensive restoration projects to kind of resist some of that susceptibility moving forward. The other cool part that comes from this preliminary analysis is we were then able to actually pull out long-term effects of some of the other expected climate change impacts like fire. So what you're looking at on the top left here, the white border is the boundary of the 1988 49er fire. By the year 2001, a lot of that area was still recovering in kind of a shrub-scrub stage. But by 2016, we saw a conversion of that back to conifer forest. And we saw a resulting shift in things like stream temperature related to tree cover versus shrub cover. So we can detect those changes at kind of long time scales and large spatial scales. This is important when we think about forest health. So when we talk about climate change, it's not just warming temperatures, it's kind of the combined impacts of increasing drought intensity and frequency across the landscape. These images were taken from some research plots in the Southern Sierra, where every tree you're looking at here that's brown is effectively dead because conifers are evergreens. They don't lose their needles in the fall like deciduous trees do. And so these trees are no longer photosynthesizing. This area actually burned then in the creek fire at very high severity because all those dead trees you see in the back form a large amount of dead dry fuel. Add to that increasing climate change impacts on things like pests. So bark beetle are a native pest in California conifers. They kill trees by burrowing into them, carving out a nuptial chamber, laying eggs. Those beetles then start to, the larvae start to then munch on the sugar-rich phloem of the tree, effectively girdling it or ceasing sap flow and water flow. Trees defend against this by pitching them out or flooding them out, like in this image here, with carbon-rich resin. That carbon-rich resin, though, is expensive to make, and under drought stress, which is increasingly likely during climate change, trees close stomata, the pores on their leaves, to limit water loss, but that limits carbon uptake. So they can effectively starve themselves of carbon by kind of having to choose between defending against drought or bark beetle. Add to that, that under climate change, we have increasingly warm winters, and warm winters are unable to keep bark beetle populations at bay. We need those cold snaps to kill those native pests. So these all then feed drought, pests, increasing aridity, just some of these larger climate change impacts and smaller indirect impacts into obviously things like fire. So again, these two images taken from the Dixie fire and the Caldor fire are actually showing two different severities of fire that really reflect both increasing climate aridity, decreasing fuel moisture, but also some of that history of removing indigenous burning from the landscape, as well as potentially not allowing some past fires to burn. So this then combines a history of management with understanding how climate change impacts moving forward might influence fire likelihood. We can use some of the local fires we've experienced as an opportunity to learn further examples of this. So the Jones fire, we have a unfortunate, unique experience with in losing our office to the Jones fire. We're just now becoming reestablished in a new office space. But ecologically, it was also an opportunity to dig back into what's the fire history on this landscape and how might climate change interact with that fire history. So this is the fire history going back to 1878, where we can see the only area that burned in the Jones fire that had been previously burned was in the 1988 49er fire. Most of the landscape, in fact, hasn't burned in over 150 years. If we use some tree ring reconstructions, we can go back and piece together what's called the fire return interval, how often fire used to burn on this landscape. And we think it used to be about every decade. and the two ecosystems that are most predominant here. So it means every decade we should be expecting the same location to burn at low severity to keep those fuels down, and this is what these systems were adapted to. So there's a fire debt in the system of 10 to 100 years. That's a buildup of fuels and unburned landscape. Add to that the climate change impacts of increasing fuel dryness, aridity, and increasing basically fire season length because of temperature. And we have projections like this, where by 2099, we expect either an 11% increase in large fires across the landscape under the best case scenario, up to a 55% increase under one of the worst case scenarios. Really what I also want to kind of come back to and end on here is the idea of case studies, the idea that we're still learning in real time. And what we learned from the Jones fires, we can use some of these really cool spatial tools to ask, how did management activities, but also potentially climate change impacts, such as drought, bark beetle, and other impacts on forest structure, influence resulting burn severity? And then can we use that to plan for mitigation strategies moving forward at that landscape scale when we talk about watershed health under climate change? We can do these same things with, for example, the river fire we're working on analysis, the Tamarack fire. So there's a few different examples of how we can combine our understanding of climate change impacts and management to better try to plan for the future. And so all of this just comes back to me to kind of end here on, I know there's a bunch of information pretty dense in there, but on this slide that I like to end these talks on, which is a quote from Einstein that says, if I had an hour to solve a problem and my life depended on the solution, I would use this first 55 minutes determining the proper questions to ask. And really, I think one of the main points that I would propose to all of you is that when we're examining climate change impacts, we need to basically use every opportunity to ask more questions, to learn more, and that can then help us move forward. So with that, I'll take any couple of questions now for a few minutes, I think, and then we can hold off on other questions till the end.
Okay, so remember to put your questions in the Q&A if you have some.
While we're waiting for questions to come in, I have one. So thanks, Jeff. That was a really good presentation. Wolf Creek and Deer Creek are neighboring watersheds. And so do you think that the results from the Deer Creek studies that you've done kind of are mirrored in other watersheds in our area?
Broadly speaking, yes, we expect some similar trends. So like I was saying, we expect increasing water temperatures, which would then lead to decreasing dissolved oxygen. We've talked to partners at Circle who have seen similar trends in their data. But in terms of land use impacts, those are actually going to be this combination of pretty large scale and also kind of catchment scale. So Deer Creek flows more, kind of east to west. Wolf Creek kind of has a combination of east to west and north to south. So topography and just local geography are all going to influence some of those land use impacts. So I would definitely recommend digging into an analysis at that scale for Wolf Creek to see what would actually be changing. But that's not to say some of these broader impacts would not actually be observed in a similar watershed. Yeah. So climate actually effects would probably be similar, but then the mediating effects of local topography would be a little bit different.
Hey, Greg, could you do the questions? Because for some reason, the questions are popping up in the far right corner of my screen.
Okay, sure, I'm happy to, yeah.
Wow.
So I'm just fielding the questions for Josie, but let me just go ahead and read them. Tom has a question. He asks, have any mitigation measures been initiated in the Jones Fire area?
So glad you asked that. So we actually, Sierra Streams Institute, had been working with the Jones Bar Firewise community, including the Woolman School and a couple other surrounding schools prior to the Jones Fire, to secure some funding from CAL FIRE and some other sources to work on some fuel reduction and forest management plans. Ironically, we got rejected the first time around, flipped the funding over, or the grant opportunity, into Wildlife Conservation Board through the state of California, and did receive that funding. But unfortunately, the funding literally came through after the Jones Fire hit. So we had put this plan together to work with the community on forest management, then the fire hit, but now we're using it as an opportunity, again, to learn what drove fire severity and actually then take what we learned in the areas that did burn and apply those across the entire community there, across all those other private parcels that didn't burn, and also focus on post-fire restoration. So yes, there's a lot of mitigation efforts kind of going on in that area right now.
Catherine has a question, I think related to that graph where you showed the different types of forest and the fire likelihood. And her question is, did you say that every 10 years we should expect the fire to return to an already burnt area? If that's true, how can an area evolve from bare dirt to conifer forest?
Yeah, it's a wonderful question. So yes, every 10 years we would actually expect fire to burn through the same landscape. And if you ever go through a low severity burned area, one that's either been prescribed burned, or it's the edges of a fire, or an area that just didn't have much fuel, maybe grassy fuels, when it burns, as soon as the following year with low severity, you actually get a pretty big flush of vegetation using all of the nutrients that were released by that low severity fire. And in conifer forests, they actually need that fire to clear out gaps, clear some of the litter, sometimes to open cones depending on the tree. And so that's actually how fire assists the conifer trees with actually growing up into a full conifer forest. When we say that Sierra Nevada forests are adapted to fire, some of them actually need fire to turn into full conifer forests, but low severity. These high severity fires can keep them from that, or you have full loss of forest canopy cover and what we call a type conversion to more shrubby landscapes. Yeah.
So the fire that she's imagining are these crown fires that are just super intense. So what's the difference between what you're talking about and what we're experiencing, or what it makes the news?
Exactly. So these crown fires that are really intense, again, these are actually portions of some of these other fires. That's why I like showing that picture of the Caldor fire, is the Caldor fire got a lot of press for some loss of homes in some high severity areas, especially Grizzly Flat, Echo Ridge. But in some of the areas that either had prior treatments or prior fires, or just a pretty cleared out understory, the fire burned down into that understory and did what fire is supposed to do, and actually burned at a lower severity. Just cleared out some of those fuels, and the overstory trees are nice and healthy. In these higher severity areas, yeah, you get pretty much a complete scorching of some of that top layer of soil. And this is why these high severity fires at large scales are such an issue. You can get, again, what's called type conversion. It can become no longer forest. So forest needs fire to get to this kind of climax forest stage. But then if you have high severity fire, then you destroy the forest and revert it back to a shrubland or some sort of moonscape. It can eventually get back to forest land, but it's going to take quite a while.
I am just a follow-up question. That so, given that we have forests that just have huge fuel loads right now because of suppression of fire, how do we move from the forest that we have to forests that can sustain low intensity fires?
It's a tough question. So that's where the Forest Service and other, CAL FIRE and other groups like to talk about this idea of pace and scale of forest treatment. Unfortunately, we cannot, ever actually keep up with the sheer volume of landscape that either needs to burn at a lower severity, or if it did burn now, would be high severity. So there's some efforts trying to mimic fire in clearing out certain portions of patches of fuel. But those efforts are kind of trying to be targeted, strategically placed. Because again, it's not a matter of if, but when these landscapes are going to burn. And so it's when thinking about things like climate change impacts, placing some of these treatments in a way that we're focusing on ecological benefit, bringing fire back at low severity, knowing that it's going to burn. So yeah, really the answer is we have a lot of work to do, including prescribed burning, letting fire burn on the landscape.
Isaac has a question, and then Ms. Chaiti, luckily I'll get to yours, but this one's kind of related to the conversation we're in right now. Isaac asks, how is the frequency of past forests determined, and how significantly does it change from region to region? If it really is every couple decades, what can be said for old growth forest? What can be said for the ecological significance of the understory of forest?
It's another wonderful question. So frequency of past forest fire is determined in a number of ways. One of the primary ways is dendrochronology. So we go find either dead trees, cut down trees in some cases, or take what's called an increment borer and core into the tree. And we use tree rings, which are essentially a living record of the conditions the tree experienced, to tell us about what it experienced. Fires that are low enough severity to clear out understory but not kill a tree usually are just intense enough to scar the tree, meaning it creates a little wound that grows over in a weird way when it closes, and it leaves a fire scar in the treatment record. We can combine a lot of tree cores across regions to look at fire return intervals for either specific ecosystem types, particular locations. So yeah, your question about return interval, does it vary by region? Absolutely. So that's the big caveat there. And that figure that I had about fire return interval, really it ranged in the two ecosystem types we have from 2 to 50 years, but the median value is 10 years. So there's going to be a lot of spatial variation, but across the ecosystem type at a higher resolution, we would still expect about every 10 years. And then the question of old growth forest, that's another hugely significant portion of this. This is referring specifically to Sierra ecosystems and ponderosa pine forests, some fir forests, Jeffrey pine forests. These are fire adapted forests. If we go up into the Coast Range, into some Oregon forest types, we actually do start to get into more of those types of old growth forests, which are often, I think, used as examples of old growth. Many of those are moist coniferous forests, sometimes even temperate rainforests. Whereas the Sierra, most of what we would consider, quote, old growth, still actually needed fire to get to that condition. So if we look at sequoia groves, they need fire for their cones to open. So yes, it's going to vary from place to place, but when we talk about Sierra forests, we're talking about a fire-borne forest.
And I have one last question. Oh, another question, but a question from Ms. Chai Tea Latte. Will you please describe, isn't that great? Would you please describe the elements you plan to study for the river fire?
Yeah, so wasn't able to dig in too much to the Jones fire analysis that I had on that last slide. One of the things that we're trying to do with a bunch of spatial data is we can get really cool high resolution data sets of, for example, forest structure, canopy cover. So forest structure is how clumped trees were, how tall they are, how leafy they are, where they're distributed, and look at that structure before and after the fire, or before and after things that may have been done even before the fire came through. And that can then tell us, in concert with things like topography and wind, which areas were more likely to burn at high severity. And then can we use that information to say, hey, if we are doing some of these forest treatment plans, is to try to return forests to a, quote, healthy state, can we use these maps of where severity was higher and why to guide that? So we can say, hey, if we reduce structure in X way, then maybe we're going to have lower severity, and target that, as opposed to just saying treat 600 acres and maybe just have some blanket, not entirely successful impact. So we're trying to use it to learn what burned where and how, and have that guide future management.
Last question is from Tom. He says, is the state or other possible funders, some funding sources, looking for local groups to suggest projects to increase watershed health?
State or local, absolutely. So I mean, I think that's really one of the the goals of this webinar. Not to put Josie on the spot, but really that's these types of discussions and having people come in with different ideas is really the goal of this. We're all community science groups here, community oriented groups. So I would just say yes, completely. All of us are. The state always is as well. The state, has some different processes, but we as organizations would love to have your ideas and help push some of those ideas to the state and to help get some of those ideas off the ground. And I think David's going to talk a little bit about some of that too.
We have two more questions continue to come in, but I'm aware that we probably need to go on. Why don't I'll hold these questions to the end, and if when we have time, I just want to give David some time to answer. So Eric and Isaac, I see your questions and we'll hold them.
Great, thank you guys so much. And sorry, my dogs just got excited there.
We can't really hear your dogs, but thank you.
Okay.
Thank you so much, Jeff. That was great. So I'm about to give you a brief discussion, not a discussion, just a description of the watershed for those who aren't familiar with it, just so you know where you are when David's talking about it. So we are in the Wolf Creek watershed, and this is where it's located in California. We're part of the Bear River watershed, a sub-watershed of the Bear River. So this is Highway 49, this is Highway 174. We're not the largest sub-watershed by any means, but we are the center of population. We have the densest population of any other parts of it. The rest are more rural. So I was having a hard time seeing all my screen here. So NID uses Wolf Creek as a conveyance, and it in water around right through here, Whitewater Creek, and takes it out down here by the tar ditch. I think I actually, yep, I jumped slides. There we go. Okay. So the creek itself is from where it starts on Banner Mountain down to where it flows into the Bear River is about 23 miles long. There's another watershed here. This is the South Fork of Wolf Creek right here, and Woodpecker Ravine. This is 174. So this is the lower Colfax Road area, and Highway 49. This is the ridge of Wolf Mountain right here. And yeah, so I live right there just for it. And so Banner Mountain is about 3,100 feet. We go down to about 1,000 feet at the Bear River, and there are about 26 named tributaries, but as you can see, there's lots of little rivulets in there. Oops. Oh, great. It's not advancing. So there we go. Okay. So it flows into the Bear River. It then goes through Camp Far West, then to the Feather River, the Sacramento River, into the Bay and the Delta. It's a little more detailed hydrology. You can see these red lines are the ditches. So we have some major ditches here. You're just seeing a tiny part of the DS Canal that brings water from Deer Creek. So this is Banner Mountain. This is Banner Lava Cap, really the ridge line. And the other side of that is Deer Creek Watershed. So they take water out of the Deer Creek Watershed, put it in the DS Canal, and feed a lot of farmers. So another major ditch here is the tar ditch. So I said that the NID puts water in up here and then takes it out right here and takes it out to Penn Valley to lots of farms. This is Rattlesnake Ditch. And then we have in Empire Mine, there's two tributaries that feed. This is South Fork Wolf Creek and Little Wolf Creek. French Ravine, Rattlesnake Creek, and Salt Creek coming into there. Many others. About 18 sub-watersheds within Wolf Creek. And then as far as plant communities, and David's going to address a lot of these, this is just context for you. So you can see that there's a change in the vegetation right along here. And this is also a change in ecoregions of California. It's the Sierra foothills region. And up here is the Sierra Nevada proper, so ecoregion. So this lower region has more oak woodlands, especially blue oak woodlands that start to drop out as we go farther north. These gray areas are just urban. This is Alta Sierra. This is the city of Grass Valley. See, so yeah, so up in here we have more ponderosa pines, more incense cedar. There's plenty of black oak, but you start seeing less and less blue oaks. Climate change, as we're discussing in many ways tonight, is affecting our watershed for sure. We had a fire just a couple of weeks ago, and the Bennett Street fire was in our watershed. We have flooding. We don't have a reservoir on our creek, but we are certainly affected by the drop down in the Scotts Flat Reservoir and dying forests. Jeff was talking about dying conifers and changes in species composition. In South County, we're seeing a fair amount of dying and very stressed out trees again this year. So we're kind of on the edge of that ponderosa pine belt where, I mean, we're having less and less of them. Extreme weather events is also another result of climate change. And some of you will remember the giant sinkhole of January 2017 right here. This is a combination of older infrastructure and, in this case, a culvert, a failed culvert, and huge amount of rain, unprecedented amount of rain all at one time in January of 2017. So this is Freeman Lane, and this is the original sinkhole. They started grading it. Now it's the Wolf Creek, part of the Wolf Creek Trail, one of the entrances. This is South Wolf Creek in the southern part of the county. And sometimes in dry years in the past, it would dry up for about a month in August, September. Sometime in August it would dry, and sometime in September it would start flowing again. But this year it dried up in June, and we don't, of course, know when it's going to start flowing again. Part of the problem is that NID sells as much water as they possibly can out of that creek to customers. And this, this creek right here is Rattlesnake Creek. And I have not personally been watching Rattlesnake Creek for very long. We only started monitoring it maybe 6 years ago or so, but we haven't seen it go dry in that time, and it's dry this year. So, and then water quality, as Jeff's been talking about, the temperatures are definitely lower in the lower reaches of the watershed and in some smaller tributaries. And so we see a real dive in dissolved oxygen, especially in South County. And there's this threshold of 20 degrees, which we are always straddling in the summers. And so we're definitely seeing increased temperatures and lower dissolved oxygen in the southern part of the county. And that's all, and I will turn it over to David.
Okay, then I will start with my screen share. We'll start presenting. All right. Well, thank you very much, Josie and Jeff. And I also want to mention that Greg Thrush is also supporting us, so thank you very much to Greg for this. My name is David Whitehead, and my presentation is following up just what challenges are we up against and what actions can we take now. I'm the group leader of the Nevada County chapter of Citizens Climate Lobby. Specifically, I'm trained by CCL to be a climate advocate. My goal is to get people communicating and connecting. And today you're doing a great job participating in the workshop using the Q&A and chat. And also we'll be taking a couple more polls during my presentation. I really want you all to feel that you can contribute. So just take a moment now to prepare yourself to contribute some more. Post your questions in chat, and then we'll get to those at the end of my presentation. Thanks. I'd also be remiss if I did not recognize that I've been assisted in preparing much of the technical information for today's workshop by my brother, Tom Whitehead, who is a hydrologist and is attending. And thank you, Tom. Okay, so here's my picture, and let's move right on. Forgot that one. Okay, so today we'll start at the global scale by discussing temperature change and its relation to greenhouse gas emissions. Then we'll take a look at our relationship to that change and what the term resilience means in general within the Wolf Creek watershed and to our community. Finally, we'll talk about actions that we can take to increase our watershed's resilience and our community's resilience to climate change. Well, anyone who's lived in Nevada County for a while knows that the temperature can vary over a wide range during any given day, over the year, and from year to year. And this slide is a way of capturing some of that variability. The lines indicate the average high and low daily temperature, and the shaded bands indicate a range for a given day. Over many years, the high and low daily temperatures have each tended to vary over a range of about 30 to 35 degrees Fahrenheit. That's 19 to 22 degrees centigrade. And that's a fairly wide range. But the problem is that small changes in global average temperatures can result in rather large changes in global weather patterns and polar ice and ocean currents and other effects. Also, some plant communities can survive short departures from average conditions, but are not well adapted to long-term changes. So we have to understand what is going on with global temperatures to understand what is going on in the Wolf Creek watershed. All right, so global temperatures over the last 1 million years look like this, and this is about the time that human species have lived on Earth. There are two scales here. On the right half of the graph, we have our recent history of 20,000 years, and on the left, the scale is more scrunched up and condensed. And note that during the last million years, there have been some pretty large fluctuations in global temperature, but also during the last 10,000 years, global temperature has remained relatively stable. And then over here on the far right-hand side is the next 80 years that's ahead of us. And temperatures are predicted to surpass anything that has happened in the last 1 million years, and it's happening at an unprecedented rate. Why? Well, the Mauna Loa Observatory in Hawaii has been measuring atmospheric CO2 concentration since 1959, when it was about 317 parts per million. It is currently about 415 parts per million, and about half of the increase in the CO2 concentrations in the atmosphere since the beginning of the Industrial Revolution has occurred in the last 40 years. So this slide shows the rise in the atmospheric CO2 concentration, which is the red line, from the beginning of the Industrial Revolution to now. And it's plotted against annual global carbon dioxide emissions, and that's the blue line. And it's in billions of tons. The graph shows actual emissions up to 2019, the year NOAA published this graph. Due to the pandemic, CO2 emissions from the energy sector actually declined by about 2 billion tons, as shown by the bright blue line here. This demonstrates the impact of a steep drop in demand for fossil fuels. However, atmospheric concentrations have continued to rise and are currently at historical high levels of 415 ppm, and that's perhaps reflecting the effects of emissions from large fires around the globe in the past 2 years. CO2 emissions from forest fires have not only significantly added to overall CO2 emissions, but have also reduced the potential for carbon sequestration by reducing the number of living trees. This graph Jeff showed you before. It's from the IPC assessment report AR6, the most recent report. It shows more detail on temperature change, particularly during the last 170 years since 1850. The vertical scale shows temperature change compared to a baseline representing the average from 1850 to 1900. The graph on the right shows the contribution from human sources of carbon emissions, most of which occurred in the last 50 to 60 years. And I'm sure you noticed it when Jeff showed you this, but just look how closely the observed line follows the simulated human and natural line. And that is a correlation and perhaps an attribution. And the IPC uses several scenarios with different assumptions about future emissions in running their climate models for the report. And these descriptions are fairly brief. I don't really have time to go into all of this tonight, but I encourage you to read the report if you want to understand these scenarios. And we've posted the link to the report in the chat. So if I graph out some of these, IPCC graphed it out. Here's how the 4 scenarios look when compared together. Now, RCP, for your information, it means representative concentration pathway. And the numbers following it refer to the amount of radiative forcing that's assumed in the model. Radiative forcing refers to the net excess energy gained by the atmosphere from sunlight. So look at the 4 lines here representing RCP 2.6, 4.5, 6.0, and RCP 8.5. And these are all increasingly radiative forcing. These plots show graphically how different emissions reductions would affect our atmosphere when considering the horizon of 60 to 80 years in the future. And you can see that only RCP 2.6, which represents a significant emission reduction scenario and correspondingly low radiative forcing, will ensure that our global CO2 concentration remains below 550 ppm. And in fact, when you see that graph, it's actually diverging away from and reducing away from 550. Okay, so let's look at the temperature data now. Here are global temperatures. These are the global temperature changes under 5 socioeconomic scenarios from the IPCC report. And this table shows near-term, mid-term, and long-term global temperature changes. Note that all the models result in levels that are within the Paris Climate Accords in the near term over here, or at least pretty close to the Paris Climate Accords. But then they begin to diverge upward in the midterm. And then when you get over to the long term, it's only in the long term, which is from 2081 to 2100, that 3 of these scenarios result in very alarming increases in warming. The worst case scenario is 5.7 degrees Celsius in 60 to 80 years. Jeff showed that as 7 degrees Fahrenheit. But 60 years does not seem like a very long term to me. So with this global picture in your minds, we need to apply this to our own local experience. And I'm now going to bring our focus down closer to home. How does this global phenomenon show up in our local areas? Well, it turns out that you can see how temperatures will affect our watershed at the CalAdapt interactive website using climate models similar to those used in the IPCC scenarios. And I've posted a link to the CalAdapt website in the chat so that you can go check it out yourself. And I also want to remind you of an earlier point that I made and also Jeff made, that climate change impacts are characterized by significant variability. So when we're looking at averages, we won't really be able to account for the extremes of climate change. Here's a map showing the average of the historic maximum temperatures in each HUC 10 watershed throughout California between 1961 and 1990 from the California Department of Fish and Wildlife's CalAdapt website. You're looking at annual average maximum temperature. The arrow points to our Wolf Creek watershed, where temperature is, as an average maximum temperature, it's 21.3 degrees Celsius or 70.3 degrees Fahrenheit. Note that the Wolf Creek watershed is on the margin of a warmer area, the Sacramento Valley. Now, here's how the annual average maximum temperature is expected to change under the mid-century medium emissions scenario, RCP 4.5, which represents, again, a moderate future warming scenario. It projects that 2.3 degrees Celsius or 4.1 degrees Fahrenheit increase in the Wolf Creek watershed by 2050. Now, a 2.3 degrees Celsius increase in the average annual maximum temperature probably doesn't seem like much given the wide range in the temperature that we are used to seeing each day and over the year and from year to year. But that's not necessarily how the plants see it. So let me toggle back and forth a couple of times so that you can see how the Sacramento Valley climate will expand into the foothills and how the cooler areas at higher elevation will contract. And you can see the way the reddish areas expand and the bluish areas contract. Okay, so now let's look more closely at the Wolf Creek watershed. Here it is, and you've seen this before from Josie. Hers is actually a lot better than mine, but I've got a zoomed in so I can show you some more detail of this. And I would just want you to look at the orange line there, this orange line marks the boundary between 2 different biological subareas. The lower portion of the watershed down here is dominated by oak woodlands, and the upper portion of the watershed by ponderosa pine forest. As the temperatures increase, the conditions that favor oak woodlands will move farther up the watershed. And as we have seen earlier, the time frame for climate change is expected to be on the order of a few decades. However, it takes a while longer for a plant community to migrate into a new landscape, probably longer than the climate change time frame. The pine forest will retreat upslope, we know that. But what takes its place over the next 80 years as the CO2 concentration in the atmosphere rises to 550 parts per million? And how quickly will Wolf Creek's plant communities adapt to the rapid changes imposed on them? And what will that adaptation look like? And here's a list of some of the impacts that we might expect to occur locally from climate change. We've talked about these earlier, both Jeff and Josie were talking about these. It's not a complete list. We've already seen indications that these changes are underway, though you may not have attributed them to climate change. While rising global temperatures will continue to be the underlying cause of impacts like these, the exact relationship between global temperature increases and local impacts is complicated and unpredictable. And so far, it's been relatively easy to ignore. So how resilient is the Wolf Creek watershed to the changes that are underway? And resilience is a term that's used a lot lately. Jeff gave kind of an ecological way of defining resilience. He said it was the ability of a system under stress, an organism under stress, to maintain its function, resist the change, and then recover. We think of it as the ability to bounce back from temporary extremes, like for a forest to regenerate after a fire. But another example is that we buy insurance to increase our resilience in the face of unusual but expensive occurrences. So what kind of resilience do we need in order to face climate change? Well, we've mentioned ecological resilience, of course, and we must also recognize social resilience. Economic resilience is another type of resilience that's very important to most people. And we also need to consider our own personal resilience and our ability to model resilience to youth. So you may have a notion of your own of resilience that's different from others. And we all place different priorities on these various forms of resilience. But any kind of resilience requires planning and resources. Resilience is enhanced by education and communication. Developing redundancy in our systems increases resilience. And once a community employs resilience concepts and is able to bring some resources to bear, then preparation can make the community more able to limit damages and able to survive the change. But we should also be flexible about our standards for the watershed. That means that if you figure out where the watershed is going to change and then do things to maintain a beneficial human connection to the watershed, that beneficial human connection draws the community and its resources to the watershed. And that process could result in Wolf Creek becoming a resource that provides an increasingly meaningful contribution to our community, even more so than now. So as far as resilience of Wolf Creek in terms of terrestrial vegetation, the California Department of Fish and Wildlife website has some interactive viewers so that we can see how resilient the watershed looks. These are map-based viewers, so that show terrestrial features with model results superimposed. And we will now look at the terrestrial climate change resilience as defined by CDFW. And we posted a link to these viewers in the chat so that you can go and check them out yourselves. And here's what you'd see. There's the CDFW's map showing the levels of resilience of terrestrial biota to climate change in the region surrounding the Wolf Creek watershed. Resilient areas are areas where conditions will remain suitable for the current array of plants and wildlife that reside within a hexagon, and where ecological functions are more likely to remain intact. And you can see some of these hexagons up here that are darker in color. Well, that means that they have a higher resilience. But then down here, these yellow ones have a low resilience. Okay, so conserving refugia is an important part of adaptation planning and a means of building resilience to climate change. And this slide indicates that the California Department of Fish and Wildlife has identified the terrestrial biota in the Wolf Creek watershed. And in fact, within similar watersheds along the entire margin of the Sacramento Valley, as having low resilience to climate change. This assessment suggests that the current array of plants and wildlife may not continue to function intact in the way that we know it right now. And note that this assessment is based on the moderate emissions reduction climate model, RCP 4.5. So let's take a moment to consider the implications of this assessment based on what we know. We're going to take a poll, and we'd like you to consider the following. When you think of spending time, labor, and money on building resilience to climate change in our community or in the Wolf Creek watershed, or both, what kinds of resilience would you want to prioritize? And I've listed over there the kinds that we've talked about, but if you want to mention other kinds of resilience, please do. And Josie, would you put the poll up if not already done so? So please take a minute to write your thoughts down there in the poll. And also go ahead and after you're done with that, write any questions or comments on resilience in the Q&A before we go on.
Just I think that the poll that you have up right now is the personal contacts with elected officials.
Oops.
So
Oops.
reflect.
Wrong one.
Almost, but I read that out, and so I'll read it to everybody again. When you
Okay.
think of spending time, labor, and money on building resilience to climate change in our community or in the Wolf Creek watershed, or both, what kinds of resilience would you want to prioritize? And I think in that poll, the answers were correct.
Yeah, just the question was wrong.
Oh, you're kidding. Oh, no.
That's okay.
I'm sorry. Okay.
All right. So have we got that poll?
Oh gosh. I'm sorry. I've got things popping up in my. It's very sad.
So everyone should use this poll to answer the question that's on the screen, although the question on the poll itself is not the right one.
That's cool. Okay, so people are responding. When you think of spending time, labor, and money on building resilience to climate change in our community or in the Wolf Creek watershed, or both, what kinds of resilience would you want to prioritize? Ecological, social, economic, personal, youth, or other?
I think we might have a problem because in this process, Josie had to close the poll, and so she may not be able to reopen it.
All right.
So wait, which one am I supposed to?
Well, that same poll that the David 1 poll, even though the question was wrong, only like 4 people had a chance to answer it before you closed it because.
Oh, I could read.
Can you reopen that one?
Yeah, sorry. There we go.
All right, everybody.
Cool. Here we go.
Make your choices known, and thanks for your participation.
Oh, there we go.
Okay.
So far, only half the people have answered, but doesn't look like any more are answering.
All right, well, let's go ahead and move on.
Okay.
All right. Thank you very much for everybody who participated in that. That data is important to us. Okay. Now mine is, there we go. Okay, so what if we don't do anything now? What if we do nothing? What if we do not decrease greenhouse gas emissions in our atmosphere? Right now, are we like these people down here waiting for the geysers up in Yellowstone? Well, if we continue with business as usual, with no emission reductions, we learned today that global temperatures are expected to rise as much as 5.7 degrees Celsius, or almost 7 degrees Fahrenheit in about 80 years. But even if we achieve moderate emission reductions under RCP 4.5, this will still likely bring us to 550 ppm by 2050. And what would this mean? Well, population migration away from the hottest areas would upset social and political relationships. And we're seeing this happening now. Also, global food production and nutritional value of crops would probably drop significantly at this level of CO2 and temperature. Agriculture will likely struggle to sustain populations, primarily in the third world. It looks like the USA is more able than is the developing world to withstand these conditions. But we really do have a moral obligation to our fellow human beings. We are rational beings and we are spiritual beings. Our spiritual histories tell us that we are obligated to care for humans, animals, forests, jungles, and all the ecological areas that create a livable planet. And the number of people who recognize this now and want to do something now is growing. And with the release of the IPCC report, there is an alarming realization that the predicted outcome of climate change described in these scenarios is unacceptable. The pathway to avoid that outcome is written in the IPCC report: reduce greenhouse gas emissions as soon as possible. But our entire world is highly dependent on fossil fuels. Although in 2020, we demonstrated that we're not quite as dependent on them as we may think. Well, the companies that produce energy from fossil fuels are really highly entrenched in our economy. So what should we do? At the local level, we could begin to pay more attention to how climate change affects our environment and our watershed in particular. Wolf Creek Community Alliance has been engaged in stream monitoring to evaluate the effects of our daily activities on water quality, but we really don't have granular and specific data over time about changes in the terrestrial and aquatic biota in the Wolf Creek watershed due to climate change. If we had a fine-scale vegetation GIS map, we could monitor how vegetation within our watershed changes over time. That would direct our tree planting program so that we plant the most appropriate trees in the optimal locations. Plus, the climate change monitoring program would enlist citizen volunteers and would encourage greater awareness of climate change at different scales. It might also provide opportunities for community groups and local agencies to work together and look for imaginative solutions that reduce our vulnerability to climate change. After all, across the country and throughout our history, it's community organizations that are often the inspiration for effective action. An idea that Josie wanted me to mention to you is the idea that Wolf Creek Community Alliance could be applying for CAL FIRE Forest Health grants. These funds are available to organizations proposing projects that promote forest health. The Fire Safe Council of Nevada County was recently awarded nearly $5 million for one of these grants. One of the requirements of the grant is connectedness within the watershed and forest. The Wolf Creek watershed is almost all privately owned and urban. And it turns out that fire-wise communities can serve as an indicator of connectedness. So if you have lots of contiguous fire-wise communities, you get points for that on your grant application. Plus, the more fire-wise communities we have, the more protected we are from wildfire. So here's something that volunteer activists can do. We could organize and contact and communicate and educate the landowners to the value of establishing fire-wise communities within the Wolf Creek watershed and help them to satisfy the requirements. It would take a team of dedicated volunteers working together over a period of several months to make these kinds of polite and respectful contacts with people. And you can see from the map that there is really quite a bit of properties within the watershed that are not part of fire-wise communities. We could also make a more concerted effort at outreach to our local government decision-making bodies. At CCL, we call this grass-topped outreach. Wolf Creek Community Alliance would establish a presence at the regular City Council and Board of Supervisors meetings, participating in the public comment period, and then commenting on various public hearings. Volunteers would establish relationships with elected officials to raise the profile of Wolf Creek watershed's vulnerability to climate change impacts. And a team of volunteers would staff public meetings, and they could also attend various community events to do further outreach. And we could also jump up to the state and national level, where we would engage local district offices, congressional district offices. Well, here's where CCL does a lot of our work. We can contact our state and federal representatives by phone or email, and we can even visit their district offices. We can attend CCL conferences to become more educated climate advocates. We can lobby both at the CCL biannual lobby days and year-round at the local level. Our CCL staff is working year-round, all the time, lobbying in Washington, D.C. to promote our goals of a more livable planet. And I'll just point out, this is our actual, right there in that picture is our actual lobby team in Doug Lamalfa's office in Washington, D.C. about 3 years ago. All right, let's see here. Okay, so now I would like to pose another question for you, and please take a minute to write your answers in the poll that Josie is going to put out. So please consider the following. What kind of action appeals to you? Decide to take one action or be involved in one group taking action and write it down in the Q&A. And this will help WCCA moving forward with our climate action program. So please select one of these options in the poll. There's the poll. Just give you a minute for you to take that poll. And I thank you very much for your input. It's really, really important to us to understand what kinds of things that we can organize for our community to actually start to do some more effective action here. All right, I'm going to go and move on. Are we almost done with the poll, Josie?
We lose Josie?
Sorry. Yeah, I think we'll stop it. We'll give you, I'll count to 10. Okay. Can you, oops,
Yeah,
you
looks
can
like,
see it, right? Okay.
looks
So-
to me like people like all the ideas.
Yeah. Yeah. And
Really
some,
how broad, I mean, people have interests in all of these areas, and almost except grass tops engagements is more than most, but all of them are sort of pretty equally representative in people's interests. That's fabulous. What that
Yeah.
means is that we're going to cover all the bases.
Well,
yeah.
thank you all for your input.
Okay.
And moving on. Okay, so talking about climate change is essential. We need more people who know more about climate change and its impacts to talk to other people. We are not isolated individuals. All these, and we're not an isolated community either. All of these climate change impacts we have talked about today apply to all of us across California and the USA. We must reach out to others in order to create and sustain the kind of societal movement that will result in legislators and corporations changing our fossil fuel dependent world. So that's what we're all about. And we really need everyone's help for this. So thank you very much. That's the end of my presentation. And we'll take some questions now.
Okay. So Greg, can you?
Yeah, sure. Can you? My internet connection's better. Let's see. Let's organize things here a little bit. So David, Christy asks, has our local climate change lobby chapter taken a look at or taken a position on the proposed reopening of the Idaho-Maryland line?
No, we have not. And that is because the Citizens Climate Lobby, when we're working as Citizens Climate Lobby volunteers, we are instructed to keep our focus. And so we really try to keep our focus on our core efforts, which is, outreach to the local community, outreach to the elected officials and business leaders, and lobbying to district offices. And specifically, I haven't mentioned it, but we do have a preferred piece of legislation and about another 10 or so pieces of legislation that we support. So that's really the focus of Citizens Climate Lobby. And that's about as much as I can say as a representative of CCL.
Good, thanks. Ray Briers has a question. When you listed the sort of partner opportunities that we had, he didn't see the BLM, Forest Service, people like that. Are those also interested parties that we should consider interacting with?
Sure. I mean, I feel that you know, any kind of collaboration, connection with people who are you know, in a position to either know about climate change or to do something about climate change, I think is a really beneficial activity. I don't really know anybody at the Bureau of Land Management, but I certainly would be willing to meet with them. I listed the ones that I think are important within our local community, and that's why I put in there NID and Bear Yuba Land Trust and Circle and Sierra Streams Institute, Wolf Creek Community Alliance. Those are the ones that I know about. And I agree that I see a comment there about Sierra Business Council, and that's true. We have lots of really good local nonprofits that we can collaborate with.
Good. I have there's a couple of questions I think are directed towards you, Josie. One is a question from Lanny asking, are we experiencing more algae blooms due to warmer water? And then another question, I think related, or I'm just going to ask them together. Jennifer asked, may I request a best and most inspiring definition of watershed, please?
Most inspiring. Okay, well, yes, we did have more algae this summer than usual. Especially, we noticed long, stringy green algae that I did not identify. Maybe Jeff did. Did you notice? Did they identify it in your lab? Very long algae maybe in June. It was really pretty early. And then best definition of the watershed. Do you have a nice one, Jeff? Inspiring one? I don't feel that inspired tonight. I'm inspired.
I guess, there's kind of competing definitions. I mean, the scientific definition is basically any area, topographically speaking, that all feeds down into the same stream that then feeds out into one area where that stream connects up to a larger river. So a watershed would be defined by the ridge tops, where every bit of rain that hits that ridge top flows down into the watershed. So wherever that boundary is. But I'd actually defer to a conversation that we had through the Yuba Forest Network with actually Greg, you're with the Sierra Fund. Carrie Monahan brought this up. We had talked about how watersheds are often defined or controlled by impacts well beyond that actual physical boundary as well. So maybe a more inspiring or realistic definition would be really the landscape or region which we are interacting with and that we have influence over, and that then directly feeds back to and impacts us. So.
Yeah, especially here where we're moving water all over the place from one watershed to the other. I think down in Auburn, there's places where people get their water has 5 different large watersheds that it comes from. American, Yuba, Bear. Some people call the Bear River the 4th river of the Yuba watershed. We have a lot of Deer Creek water in our watershed. It's really, yeah.
They're all interconnected, absolutely.
I think this is a question for David from Doug. He asked, how did Representative Doug Lamalfa respond to your presentation?
Well, that's a really good question. I have to be careful because our conversations with elected officials and their staff are confidential. But I can tell you, and it wouldn't be any surprise to you, that Congressman Lamalfa does not consider climate change to be a high priority. I can tell you that he typically has assigned staff members to meet with us in our lobbying. I think earlier on in his term, he met directly with Citizens Climate Lobby people a couple of times. And I would just characterize that as, we were really trying to introduce him to certain concepts, and he had other ideas. And you've heard the things that he has said about climate change, so I don't think I have to go into too much detail about that.
Thanks. There are a couple more questions that were lingering from Jeff's presentation. Do we have time to answer them, or do we need to wrap up?
Let's see, 7:29. We could go, and people who need to leave can
Okay,
go.
Good.
Yeah.
And there's another couple of questions popped up. One for David. So I will just go ahead and ask. Isaac asks, what are the attributes of a low resilient region like Wolf Creek Watershed that make it low resilient? If only 30 year to 2050, we're only 30 years to 2050. And will this watershed be extremely low resilient by 2100 and beyond? Will it be a prairie by 2050 or 2100? And this, there's another question that Eric asked earlier. Like, he was curious about how does climate change increase the likelihood of type conversion? So forest types changing, given all other things being equal. So if you guys want to take some turns at those questions, I would be fascinated.
I'll just reiterate what I said in the presentation, is that the time frame for plant communities to migrate is much longer than the time frame for climate change, temperature changes, and aridity, and all the other impacts that we've seen. Those impacts are happening much faster than the plant communities can migrate and react. And that really is one of the biggest problems with the whole resilience concept. And we don't know how those areas are going to react. It could, I think the suggestion is that that the community will, the various biotic communities will become more and more like those that are down in the Sacramento Valley. There'll be more grasslands. There'll be other kinds of things that will survive under those conditions, but not necessarily the ones that are there right now. The flora and fauna that is there in those communities now is going to be, in a fix. Either move or die.
Yeah, I would just tack on to that really quick. One of the things that, all three of the talks really commented on, we talk about susceptibility to climate change, and they also talk about things like refugia. And there are spots in the topography that we have, being so variable, where at a broad scale, yes, we might expect this type conversion of forest to grassland, but there are certain areas, maybe they receive different amounts of sunlight, they're more north facing than south facing, they're kind of tucked into a canyon, that are more resilient to that change. And that then provides potential targets for some of this local action to say, hey, this area might actually be resilient to that change, where we might get, yes, a conversion of conifer forest to oak woodland to grassland. Maybe there's a little canyon tucked in area that we can maintain through some active management strategies that can then serve as kind of a climate refugia moving forward, so that can stay as a certain forest type kind of tucked into those canyons and preserve some of those sources, even of some of those vegetation types. And then in terms of vegetation conversion, yeah, there's still, I think the jury is still out on how quickly, some vegetation, it's basically, adapt, move, or die. And adaptation is still an option. There are some communities where we do have some resilience showing up in terms of, climate actually acting as a selective event, a selective pressure, and actually killing off the ones that are less resilient and keeping certain pine trees or oak species or oak individuals that actually are more resilient to that stress, that under maybe wetter conditions wouldn't have survived. So there is still some hope in certain areas too, in terms of some built-in kind of genetic resilience too. So we, like David said, I think there's a lot that we just don't know. So.
Wonderful. Thank you guys so much.
I think I'll give the little outro, and then if people want to hang on and ask a few more questions, then we can do it, if you guys are up to it. But
Yeah, sure.
yeah, okay. So thank you all for joining us tonight, and we hope you learned something. If you're not already involved in climate change action, please consider jumping in soon, because we need you. Join an existing group to have the largest impact. Sierra Streams Institute, Wolf Creek Community Alliance, and the Nevada County Citizens Climate Lobby are two of many groups working on solutions to local and national climate change issues and helping to build resiliency in our county. Please look in the chat for more contact information for the speakers and their organizations. If you need to copy items out of the chat, there's 3 little buttons next to each item, and one of them will allow you to copy. Okay, that's all. Thank you so much. And then if you want to hang on and ask a few more questions, then do so.
Thank you all. And thank you, Josie, for hosting this. And thanks, Greg, for moderating.
Great.
Yeah, thank you very much. I really learned a lot, and I feel like it was a really positive experience for me. Thank you very much.
Good, good. Okay, is there one question left in the Q&A, Greg?
It is. It was a question from Isaac, and I think it got covered, but I can ask it again. He asks, are local forests less likely to recover from fires with increasing climate aridity?
That's one of those things where I'm gonna couch my answer and say it depends, as always. But for the most part, yes, we expect that to be the case. Post-fire, a lot of seedlings that in the past may have received ecological benefits from fire, from clearing out gaps in the forests, clearing out duff, letting seedlings germinate, there's also less soil moisture. So if we have less soil moisture, there's less moisture for those seedlings to pull from. And we actually are seeing in some cases some data pointing towards increasing mortality of large swaths of seedlings before they get to the sapling stage. So in general, yeah, we expect that's the unfortunate coupling of, even if we have low severity fire, climate change is going to absolutely drive decreased, what we call forest recruitment, decreased ability for seedlings to sprout. Yeah.
Jacqueline makes a comment. She said, maybe we should be having living room conversations to bring climate deniers around to understanding the science. It's an interesting idea.
Yeah.
Yeah, I'd like to say something about that. At Citizens Climate Lobby, we really do understand that the conservative side of our political spectrum is not interested really very much in talking to us, but we want that. We need those conversations to happen. So it is difficult to strike up a conversation with somebody who calls themselves a climate denier or is going to give you a big argument about facts. But you have to be patient, and you have to ask people questions about that. You have to be genuinely interested in their position before they will even consider your position. So it's important to have those conversations, and I encourage everybody to try to have those conversations with people who seem to have their minds really set against acknowledging climate change. So please have those conversations.
Yeah, I was just going to say, even just considering kind of the combination scientific educational perspective, really we think of even how students learn, and one of the best ways that people learn is by being exposed to information and being guided to coming up with a solution themselves, to having ownership over the thought process that leads to an idea and a revelation, and then kind of an assimilation of that information. And so really, I think approaching any of this in a combative way is, counterproductive. And I think that just showing the data and then giving some of the thought process that we take to understanding climate and climate change, I think is really an important approach. And then really also removing this idea, I'll just point out really quickly, this idea of kind of belief. I think that conversation gets brought up a lot, of I believe in or don't believe in climate change. I know I'll just quickly point out, to me, that term doesn't apply. When we're talking about climate change, we're just talking about what data is showing us in terms of changes in global atmospheric patterns, climatic patterns, and there's no belief involved. There's belief is when you start to get into, am I taking something beyond face value and starting to assimilate it into other conversations that are not really scientific at that point. So really keeping it at the level of data and what we think we know, and also acknowledging uncertainty. That's a huge point too, I'd point out. All of this, all of the climate models that we have, there's a reason those error bars are so huge. There's a lot of uncertainty, but even with that uncertainty, we know that even our biggest errors and projections still have acknowledged anthropogenic climate change. So.
And I'll just give a little plug for CCL, is that on our website, we do have training programs, videos and whatnot, to help you to have those conversations. They're directed specifically at how do you talk with somebody who doesn't believe in climate change. They really have some pretty sophisticated techniques. So I would encourage anybody who's interested in that to join CCL and take some of the training and learn how to be kind of a climate advocate, and then go and have those conversations with people.
I think there's also disbelieving science. People don't believe in science now. I've been seeing those conversations on social media, and it's pretty disturbing. So.
Yeah, and that's again, that's a tough one for me, because I would point again to David's comment of at least acknowledging where people are coming from, as opposed to being combative against that and seeing where that might stem from in terms of thought process. And again, acknowledging that there's nothing to believe in with science. Science is a process. I think science gets often wrapped up in political conversations as what I call capital S science, as this thing, this behemoth beyond what it actually is. And really all we can do, again, is refer to science as a method, referring to data, analyzing the data, interpreting the data. What you do with that data is where you start to get into those political conversations and discussions of belief, but the data is just the data. And so I think those conversations about, quote, believing in science also should happen in a way that's acknowledging, hang on, let's redefine what you're referring to as science here. You might be referring to a scientific institution as opposed to science as a process.
And when you talk with someone who you think might be combative, a very good technique to use, it's a little hard to have the self-discipline to do this when you're in the heat of a conversation, but instead of responding directly to what people are saying to you, the claims they're making, instead think of an open-ended question that you can ask to the other person that will actually get them to describe more clearly what they're thinking about. For instance, instead of saying, do you believe in climate change, which is obviously going to get a yes or a no answer, you might ask, when you think of climate change, what kinds of problems do you think about? What kind of problems come to mind? Or when you think of the problems that are associated with climate change, what kind of solutions come to mind? Now, that's an example of open-ended question that will make a person kind of think a little bit about their answer rather than just going on with their diatribe, going on with their rant. And you're also giving them the respect and the appreciation for their opinion, for their position, for the things that they say. And that's a big part of having a decent conversation with somebody, because it's like when you get in an argument with somebody over climate change, it almost always gets personal really, really fast. I know. So you've got to really avoid that.
Yeah, because at that point, you're no longer actually talking about climate science. You're no longer having a legitimate debate. So,
yeah. Okay, I think that's about it. Unless someone else has a burning question.
Somebody's raised their hand. Oh, no. Okay, I'm sorry. Never mind.
Do that. Okay, I think that's it. So thank you all for coming, and have a good evening. And it was really wonderful presentation, Jeff and David.
Okay.
And thank you, Greg. I
Very good.
forgot to introduce you. I'm really sorry. I'm glad that you picked that up, David. And for some reason, the Q&A went way off my screen. There's like a little white corner and I can't. A lot of people had trouble signing in tonight. I got a number of emails saying they couldn't get in.
Oh, no.
3 emails, and one of them did get in and the other 2 didn't. So. Okay.
Thank you so much.
Okay, good night. Thank you very much. Good night, little doggy.
That's Nibbler.
Thank you.
Thank you.